Exploring the Solar System Part 4, looking at exoplanets. So why do we look for exoplanets? How do we go about finding them? How would we go about looking for life on other planets? And the usual question at the end, what next? Last time I showed you an orrery and we were looking at the solar system. And of course, we can ask the question when we're looking at our solar system, is our solar system typical? If we were to look at planets around other stars, do we find solar systems out there that look anything like ours? Are there any other Earths out there? Maybe looking at other planets can help us understand more about our own solar system. There are a number of ways we can find planets. I'm not going to describe them all in detail, otherwise we will be here till midnight. I'm going to describe a number of different techniques. Radial velocity, the fact that when planets go around stars, it means the star itself is wobbling and sometimes coming towards us, sometimes away from us. And spectroscopically, we can see a red shift or a blue shift of that star. That's a wobble method, if you prefer, otherwise called radial velocity. We can watch what happens if a planet moves in front of a star and dims some of the light from the star. So basically we're looking for shadows. That's the transit method. The third one I'll mention is direct imaging. Although planets are very much fainter than stars, if somehow we can block the light from the distant star, maybe we can see planets on either side of that star. The final two of these five I'm not going to describe in detail, microlensing and astrometry. They're mentioned in the handout, but I'm not going to deal with them in any great length here. But astrometry comes back to what the question in the previous talk was talking about. Gaia, for instance, the spacecraft Gaia, looking at motions of stars. So firstly, method one, radial velocity. If a planet is going around a star, that star, because they're both orbiting around the common center of gravity, the star will wobble and spend some of its time coming towards us or away from us. It won't look blue or look red, so that graphic is not particularly useful. More useful if we think about this particular graphic and think about a planet going around a star, making the star wobble. Top left as seen from above, bottom left as seen from the side. But that's what we will see. The planet causing the star to move towards or away from us will make any features in the spectrum move slightly towards the red or slightly towards the blue. It's not going to make the star red or blue, but we will see features move slightly in the spectrum. The actual velocity of the star in terms of how fast does it have to move for us to be able to see a spectroscopic movement of the star, it's tiny. In other words, the star only needs to move at a velocity which is probably less than walking pace, less than a meter per second, in order to be able to measure it with the spectrum. That's how good spectroscopy is these days. Another technique is the transit method, where a planet moves in front of a star and causes the light output of the star to change, as indicated by the graphic in the bottom left there. So we measure the output of a star, and then once in a while we find the light dips and then comes back again, indicating that something has transited in front of the star. The larger the object, the more the light will dip. So if we look at two examples here, a large planet on the left versus a small planet on the right, simply the physical size of the planet will determine how much of the starlight is dipped. And therefore, if we look at the dip, is it a 1% or 2% dip in the amount of light, we can get an idea of the size of the planet, the diameter of the planet, relative to the size of the star. If we understand how stars work, and generally speaking we do understand how stars work, we can figure out from the spectrum of a star roughly how big it is, and hence we can get an indication of the size of the planet. So the wobble method that I mentioned in method number one, that depends on the mass of the planet. The more massive the planet, the more the star will wobble. Here we're looking at the size of the planet. In other words, its diameter. Now with transits, it actually works even if we have a very complicated solar system. For instance, what if we had 3 planets? Well, there, as the first planet transits, the light level drops, and then that has finished and the light level comes back again. What happens if we have 2 planets? One is starting to transit and then the other one starts. You can see the light curve in the bottom left there is more complicated. But given a bit of time and a bit of ingenuity, even if the light levels jump up and down and back and forward, we can work out what planets must be in the solar system that we're looking at to give us that particular change of light. So that's what we might hope to see for a planet going in front of the star. We might hope to see those blue dots. The more accurate data we take, the more we can trace out the white line, which is, if you like, the best fit to the blue dots that we're actually measuring. The more data we take, the better we can determine what that actual dip was, and hence the more accurately we can determine the diameter of that planet. This is actual James Webb data, giving you an indication there on the left-hand side. Perhaps you can't read the scale, but on the left-hand side where it says starlight, that's 100% of the star's output. And then at some particular point, the light has dropped, in this case, only to 99%. So only 1% of the starlight was actually obscured by this particular planet. And you can see it dips. And then after a certain length of time, in this case, an hour or two, it comes back up to its original level. So if you stare long enough at a star, then every once in a while you might see a dip like this. You have to be careful that you are actually looking at the transit of a planet. For instance, what happens if a star has a large sunspot on it? Is it possible that that could give you a temporary dip? If you do see a dip which you think is a planet, what you have to do is wait until that planet comes back again and then see it dip a second time, and ideally a third time. Then you know you're definitely looking at something which is orbiting around that star. So you do have to be careful when you look at any change of light output. For instance, are you sure that the output of the star is stable in itself? It's the shape of this dip that characterizes that is definitely the transit of a planet, rather than simply the star temporarily getting a little bit dimmer. Method 3 is the idea of block the light from the star and hopefully you see a planet. So remember that stars are much brighter than planets by many thousands, if not millions of times. Therefore, if you're looking at a star, you may not see a very faint planet to the left-hand side, for instance. But if you were to occult with an occulting disk, block out the light from the very bright star, then it might be possible, once you've occulted the star, to actually then reveal the very faint planet, maybe 1,000,000 times fainter. So it's a rather tricky thing to do. You have to have very high precision optics, a very tiny disk, not one this size, a very tiny disk in your telescope blocking out the light from the star, revealing the light from the planets. This gives you an idea of how it can be done. This is a time-lapse image where the star in the middle has been blocked out with a disk, and then we see 4 points of light. Let me run that video one more time. We see 4 points of light, the inner ones moving faster than the outer ones, just like Mercury moves faster than Venus, moves faster than the Earth, etc. So in this particular case, we're effectively looking plan view onto a solar system of at least 4 planets, 4 bright planets, maybe a few fainter ones as well. And it actually also works if we're looking at the solar system edge on, as in this particular case, where the star is blocked out, and when it appears behind the occulting disk, the planet looks easily visible. It's disappearing behind the occulting disk again, and then the planet reappears on the other side of the star. So this can be done with Earth-based telescopes. It's a little bit laborious because you have to image over and over and over again, and it might take weeks or months or even years. Perhaps you noticed that when you looked at the scale on the bottom left hand here, 2004, 2005, 2006, 2007, this is a 17-year time-lapse image of these planets moving around the star. It's not something you can just capture just like that. But it has produced a number of different exoplanets around a number of stars. Methods 1 and 2, the idea of looking at the wobble of a star and looking at transits, those are the methods that have found most by far of all the exoplanets we know about. This technique might become more interesting in the future, but so far it hasn't found that many planets. What we have done, for instance, with James Webb, again, The black disk in the middle is blocking out the light from the star, which is much, much, much brighter than this rather dusty disk around the star. If you block out the light from the star, then James Webb is able to see what's going on. In this case, it doesn't appear to be a whole load of dots indicating planets going around this star. It looks like this is a planetary system in the process of formation. Perhaps what we're looking at is a very early solar system. Perhaps that's what our solar system looked like many billions of years ago. It's almost as if we have rings, perhaps we have an asteroid belt, perhaps we have a Kuiper belt, but we don't seem to see lots of bright dots indicating we have not, in this solar system, seen the appearance of a Jupiter or the appearance of an Earth or the appearance of given planets. Oops, sorry. But if we use these methods in combination, for instance, if we're lucky enough to be able to look at the wobble of a star and see a planet transiting in front of the star, then that gives us additional information. Because if we can use multiple techniques, such as radial velocity to look at the wobble, remember the amount of wobble is determined by how massive the planet is. Whereas if it transits, it's the size of the planet that matters, the diameter. So if we're lucky enough to be able to use more than one technique to see an exoplanet, radial velocity gives us the mass, transits give us the size, and if we can look at the spectrum, we can also get information about the atmosphere, if there is an atmosphere of the planet. But with mass and size, if we can identify a given planet and find its mass and find its size, then in combination, we can find its density, which is just one divided by the other. And of course, if the density is very high, we might have found a rocky planet like the Earth. If the density is very low, like the density of 1, then maybe it's made of water. If the density is less than 1, maybe it's a gas planet. So we can get an idea of the type of planet we're looking at by measuring its mass, measuring its size, and getting the type that way via the density. We can also estimate for a planet its temperature by working out, well, we think it's that far from the star, assuming we know the distance to the star, coming back to Gaia to give us the distance to stars. If we know the distance to the star and we know how far the planet is from the star, we can say that star is a hot star, or maybe it's a cool star, and the planet is that far away, so we can work out what the probable temperature of the planet is. If it's very close to a hot star, almost certainly the temperature on the surface of that planet is very high. If it's a long way from a relatively cool star, then it's probably a very low temperature. So we can judge the temperature, and then we can say, well, it's probably more likely to be an ice planet than a water planet, or possibly it's going to be a lava planet if the temperature is really high. So with a lot of this data rolled together, we can start to put together all the pieces of the jigsaw and get a lot about what's the story of this particular planet. And we have found lots of exoplanets. That's not all of them. No, that's just a little selection of the exoplanets we've found. So far, we have discovered 6,000 exoplanets, 6,000 planets around other stars. When I was young, this was science fiction. The idea that you could possibly ever see or detect a planet around another star was pure science fiction. And now we've done it 6,000 times over. This is just 1,000 of them, roughly speaking, just to give you an idea. They're arranged to scale in terms of their size, and given that we've got an idea of temperature, the ones that are likely to be very cold are on the left, minus 200 Celsius or so, and there you see plus 200 and even higher on the right-hand side there, judged from how far away from their star and is their star a hot star. Just to give you an idea of scale, there are a few interlopers in there. Although this is exoplanets, we have a few of our own planets in there just to give you an idea of scale. So there's Jupiter, Saturn, Uranus and Neptune in the bottom left-hand corner, so you can judge how small or large some of these other planets are. If we were interested in finding life out there, then it's not necessary, but it's quite useful if we know there's any liquid water on these planets. If there's liquid water like there is on Earth, we know life has a chance. It doesn't mean that no water means no life, but if we do find liquid water, we know life has got a chance. So in terms of the temperature, we know that if any exoplanet is on the left-hand side. It's basically too cold for liquid water to exist. The water would just be ice. And on the right-hand side, there's a whole range of temperatures which are just too high. Liquid water would boil away. The Goldilocks zone, where planets would have possibly ice and water vapor, the Goldilocks zone that we would like to be in, the habitable zone, you can see is relatively narrow on this scale. There's a huge number of exoplanets that are not anywhere near Earth-like as far as the surface temperature goes. And just again to give a scale, Mars would be in that position. In fact, it is. It's actually plotted in this particular diagram. Venus is on the hot side, and surprise, surprise, Earth is in the habitable zone. Yeah, of course it is. So that's where Earth is. So if we are determined to find Earth-like planets, we ought to be looking in that strip. But of course, people are interested in what's going on across the whole of the exoplanet zoo. Let's just pick out a few at random almost, just because they are sort of interesting, not necessarily Earth-like. I thought it was quite fascinating that when we start to look for exoplanets, we find that there are exoplanets going around our immediate neighbour, Proxima Centauri, only 4 light years away. If planets around other stars are not very common, how come is it? Is it just a coincidence that we happen to have an exoplanet around our immediate neighbour star? It looks like, statistically speaking, that would be very unlikely. So although we haven't checked every star in the Milky Way, it looks like it is a very high probability that stars in the Milky Way do have planetary systems. Maybe half of them have planetary systems, is our best guess at the moment. Some of them are quite old. For instance, one has been nicknamed Methuselah, which appears to be 12.7 billion years old. This means that planets are not anything recent. Our Earth was only born 4.5 billion years ago, compared to the universe, which was born 13.8 billion years ago. But this very old planet would seem to indicate planets were around almost immediately. Not necessarily on day one, but it did not take many, many, many billions of years before stars started to develop planetary systems. As far as we can tell, as soon as there were stars, there were planets, as best we can tell. We still need to do some research on that line, but that's our best thinking at the moment. So that one, getting on for about 1 billion years after the Big Bang, and it's quite possible that when we search for more exoplanets, we find even older ones, perhaps. In the top right there is, given that the right-hand side, remember, is the hot end of this particular diagram, that has a rather balmy surface temperature of 4,000 Kelvin. For those of you who like the warmer weather, that's probably a bit too warm for most people. And this star in the bottom right, which again at the right-hand side of this diagram, so clearly close to its host star, that looks like a bit of distortion. Well, we think that's the actual shape of the planet. We can't be sure, but this particular planet is so close to its host star that the host star is raising tides and actually distorting the shape of the planet. So this egg shape is real because this particular planet is only 4 million kilometers from its host star, much closer than Mercury is to our sun, for instance. So it might well be that with some of these things with very high temperatures and some of these planets really being distorted by being close to the star, no surprise that we really want to look most of the time at planets that are further away from their host star than that. One of these, the largest one, I think it's the largest one in this particular diagram, or maybe the second largest one in the top right there, that is a planet that's larger than Jupiter, but it's less massive than Jupiter. It's about 10 times bigger than our Jupiter, but less massive. That means it must be a really low density. So we think that's got the density of about marshmallow, something like that. Very low density. Quite what it's made of, we don't yet know, but it does appear, based on its mass and its size, to be a very low density. You can see these planets have ridiculous names like HATP67b. Again, like the extremely large telescope. Astronomers are not good at naming things. But I think somewhere along the line they must have decided to have a competition. And I think the winner of the best name for an exoplanet has got to be Coconuts 2b. They've reverse engineered it to be cool companions on ultra-wide orbits. In other words, this particular group were interested in any planets that appear to be a long way from their star. And of course, if they're a long way from the star, it takes a long time for the planet to orbit. This particular one is 7,500 AU. 1 astronomical unit is the distance from the Earth to the Sun. So this planet is more distant from its star by a factor of 7,500 compared to our distance to our Sun. And we take a year to go around the Sun. It's estimated that this planet takes about 1 million years to go round. That's based spectroscopically on the evidence that we have. But I think the winner of the most weird planet that people have come up with so far, based on the evidence that we've got about its position and its mass and its radius and other factors, this has been called the eyeball planet because we think this planet is made of ice based on its composition, but we also know it's relatively close to its star. Now that sounds unlikely because surely it would melt. Not if the star is very dim. So remember, some stars are supergiants and really luminous. Some stars are dwarf stars and relatively dim. This planet appears to be around a dwarf star so that it's relatively close. And although it's made of ice, it is tidally locked to its star. In other words, like the moon is tidally locked to us, so always face the same face of the moon towards us. This planet is close enough to its star that it's tidally locked so that one face of the planet always faces the star. So although it's made of ice, one side of the planet is always facing the sun and one side of the planet is always facing away from the sun. That means it's quite likely that one part of the ice planet has melted because it's always facing the sun. So it's thought that maybe this particular object is an ice planet with a little bit of water that faces the sun, the star. So it actually looks like an eyeball. Now, okay, a certain amount of artistic license there, but there are good reasons, good scientific reasons to believe this might be an ice world where there's an ocean on the side that always faces its host star. So it's not necessarily blue and white as indicated by that, but it's interesting to think that maybe there is an eyeball out there staring at its host star. So one thing I'm trying to get across is that exoplanets are enormously varied, from the really hot ones, the really cold ones, the really large ones, the really small ones, the low density, the high density, the weird ones as well, the old ones, the new ones. We have found 6,000 exoplanets and they are essentially all different and they are all worth studying. They are all worlds in their own right, regardless of whether they have life or not. So Gaia and the James Webb Space Telescope, Gaia is not looking for exoplanets. It's mapping out the positions of stars very accurately. And in the process, if a star is wobbling because a large planet is going around it, then Gaia will actually see that star wobbling and deduce that that star has got planets going around it. So Gaia has actually found some exoplanets, as it were, by accident. James Webb Space Telescope isn't finding exoplanets, it's told to go and look. If we think they exist because of other telescopes finding them, James Webb is told, go take a closer look at this particular system. So James Webb doesn't find exoplanets either. But there are quite a number of missions that are dedicated to finding new worlds that are out there. Kepler has been doing this for more than a decade now and has found thousands of exoplanets. And if you notice the dates, there are new missions coming online relatively soon. There's an ESA mission that should be online next year called Plato. There's also a NASA mission called Roman, which, if a certain president doesn't decide to cancel it, might still happen in 2027. Yeah, it's not by any means. Just because it's well advanced in the mission does not mean it's not going to get cancelled. So there are still fingers crossed that this will actually happen in a couple of years' time. The Roman Space Telescope, named after Nancy Grace Roman, that's actually quite an interesting one because part of its mission is to do what we've done before, which is take an occulting disk, a tiny disk inside the telescope to block the light of the star and see if you can see any planets. That has the disadvantage that the really bright light from the star has already entered the telescope if you try and do it that way. And if you have a very bright star, some of that light will get scattered because optics are imperfect. No matter how good your mirror, no matter how good your lens is, if you have a very bright star light entering the telescope, some of that light will be scattered and it might make it very difficult to see faint planets. So one idea is don't have the occulting disk inside the telescope, do it differently. Have the occulting disk outside the telescope. One thought is have Nancy Grace Roman and a star shade which unwraps itself and produces a shade 100 meters in diameter. You then fly it 50,000 kilometers away until it's far enough away to just cover the star that you want to block. And if you keep them with that amazing choreography, you might find it possible to block the light from a distant star and reveal the presence of planets going around it. Because you're blocking the light at source, not the light after it's entered the telescope, in principle, you can get much better contrast and hopefully see much fainter planets. But of course, you then have the problem of the choreography of flying a star shade and trying to keep these telescope and star shade lined up. You also have the problem of how do you unfurl something that's 100 meters in diameter? You've got to pack it into something the size of a barrel first. But remember the James Webb, huge sun shield, the idea of packaging something and then unraveling it in space is actually doable. They've tested it on bits of origami and they reckon it is possible to do this. There's no fixed date for doing this. At the moment, they are going to stick with the idea of having occulting disks inside the telescope, but it's thought maybe this is the way to go for the future. I talked about looking for life. How are we going to look for life? Well, there are a number of possibilities. If we have a planet moving in front of a star or even behind the star, if we look at the spectrum of the light and the planet, when the planet goes behind the star, we lose the light from the planet and we can see if the spectrum changes. That tells us about the spectrum from the planet. Or we wait till the planet's in front of the star, in which case light is shining through the atmosphere, and then we can see changes to the spectrum because some of the light is being absorbed by the molecules in the atmosphere of the planet. So if we think about a dip, such as shown by the James Webb Space Telescope, if we do that at different wavelengths, we find the dip is slightly different. The red dots are slightly higher than the blue dots, which are slightly higher than the yellow dots. So different wavelengths will cause a different depth of dip, which tells us that certain wavelengths are being absorbed, and we can relate that to which molecules absorb those particular wavelengths. And then we can generate a spectrum of the atmosphere of a planet that could be hundreds, if not thousands of light years away. The fact that we can tell what chemicals are present in the atmosphere of a planet 1,000 light years away is a truly incredible feat. And that's one of the things that James Webb is able to tell us. At the moment, the James Webb has not found an atmosphere that tells us, yeah, this balance of CO2 and water and oxygen and methane, that can only be generated by life. But the more James Webb looks, hopefully one day it will find that. Just to finish with an indication of what has been found, this is a plot of mass on the vertical scale, orbital period on the horizontal scale, and each dot is a new exoplanet that we found. During the 2000s, Kepler was launched and then produced a huge number of new planets, the purple dots. And as you can see, as we go through the teenies and into the early 20s, we can see thousands upon thousands upon thousands of new planets being found. There's our planets for scale, as it were, or at least to give you an idea of where they are positioned. You might look at that and say, well, all the exoplanets we found are very different from Jupiter, Saturn, Uranus, Earth, etc. But bear in mind, this is biased by the fact that it's easier to find big planets because they make the star wobble more. It's easier to find big planets in terms of their diameter because they block more of the light. So it'll always be easier to find Jupiters than it is to find Earths. So we shouldn't take this as indicating there aren't many Earths out there. Quite the contrary. We think there are 1 billion Earths in our galaxy, but we just haven't found them all yet because they are more tricky to find than the Jupiters. So if you're interested in exoplanets, NASA has a wonderful web page which tells you all you want to know about every exoplanet that's ever been found. And as I've said, there are interesting missions coming up next year, the year after, and you can go to the NASA or ESA web pages to find out more about them. Thank you very much.